Sellmann, and Meinolf is a well-known person in optimization world, where people do constraint-based use constraint-based solvers, linear solvers to solve really large, serious optimization problems like supply chain, manpower management, and a lot of similar problems that requires very serious, usually very serious knowledge of optimization. And Meinolf has experience in both, in theoretical experience working for universities, and recently he started his own company with his own, he calls this revolutionary solver, and because he wants usually to bring latest advances in optimization science to real world problems. And you can listen his podcast. It's always right to the earth presentations, and I expect we will hear the same real world learning based optimization technology presented by Meinolf today. Meinolf, please take over.
Thank you so much for having me, Jakob. It's a pleasure being here. So what I want to talk about is the field of optimization and what advances we've made there at long last after 80 years that allow us to do things a little bit differently and to unlock a new value proposition. So now with optimization, lots of people associate different things. What we're talking about here is decision making. You think about running a business, say you have to set prices for your products. How do you do that? Say you're running a warehouse. You have to decide when you're going to order what, in what quantities, where you're going to put it, and when you get a new order, in what order are you going to pick up the individual items. Right? All of those things are decisions that companies need to take, often as a matter of course and very, very frequently, which is why we sometimes refer to them as operational problems. And the field behind it is, of course, operational research. And, let's talk a little bit about that field and where we're standing and what we might need. First of all, it's a very, very, there's a reason why I chose to go into that field, because it's actually a very noble profession. You're trying to make more with less. Inherently, if you improve efficiency, you're also working towards better sustainability. You increase competitiveness of our democratic societies, which is good. You turn forecasts into value, a very important one. There is a tremendous amount of investment in AI and machine learning, but they don't come to fruition. They don't actually carry any value, those forecasts, unless they influence decisions. So how do you go from the forecast to the decision, which then generates the value? That is the gap that needs to be filled. And you bring efficiency to the world. Now, the go-to workhorse that we've been using really for 80 years is mixed-integer programming. It is, if you've ever taken a computer science course, if you've taken, even if you go to business school or so, you will have come into contact with linear programs. And you'll see one in a second. So if you don't know what that is, you get a flavor in a moment. Okay, so this works for some problems, and it works very, very well. We've improved these. So the software that turns a description of what you need to decide, how to decide whether something is better and what you can execute into an actual plan is called a solver. So the software that we're talking about is a solver. And these mixed-integer programming solvers, or mixed-integer linear programming solvers, or sometimes also mixed-integer nonlinear programming solvers, they have they have their uses. If you actually know what the future is going to be like, you can optimize for it. There is a larger group here. I already mentioned the nonlinear ones where the same approach actually works. And it's essentially branch and bound, what we're talking about. It is so basically you have a relaxation-based approach that holds for all of MIP, but it also holds for convex nonlinear programming, where you see that if you start a plan, you see that any continuation of the plan is not going to improve. and then you forget about it. So you backtrack and you try something else. And like that, you're enumerating an enormous amount of potential solutions implicitly. The problem is that only works for a small subset of problems. So imagine, for example, you have a multi-objective problem. And most real-world problems are multi-objective and not hierarchical multi-objective. No, they are multiple KPIs that are in competition with one another, and there is an okay range for everybody, and then there's an excellent range for everybody. And it's not clear how they trade off against one another. There's an enormous amount of problems that are stochastic. I mean, think about it. If all the examples that I mentioned, pricing, for example, do you know how much will be bought at a certain price? No, you have no idea. You can make some forecasts, but it's not like they're set in stone, and you absolutely knew this. So if any data in a mixed-integer program is estimated by machine learning, you're immediately talking about a stochastic problem. And the relaxation-based solvers are not fit to solve them. And then there's this massive field of non-convex, non-differentiable problems that you might have that really aren't a good fit for mixed-integer program. So this is what I'm talking about today. It's like we have a workhorse, we're doing a very noble profession, but we are lacking a tool in order to tackle, the big part of this field, and not be stuck in that little corner on the lower right. So to substantiate what I was just saying, look at the textbook examples on optimization. There's even a standard library, the ORlib. There are facility location problems, traveling salesperson. You might have heard of pricing. I mentioned production planning, inventory relocation, all of the above. In the real world, we don't know where we're going to open facilities. In the real world, we do not know how long it's going to take us to go from A to B, and how long we have to stay at our destination in order to get our work done. When we're estimating prices, which is really a price demand sensitivity curve, that's usually nonlinear. I mean, the first thing that any machine learner would do is a log-log transformation in order to then fit a linear regression to the log-log. And that has good mathematical reasons why you would do that, but it's immediate, it's nonlinear. And of course, every estimate where you're saying, well, at this price, I'm going to have this demand, comes with uncertainty. This is not set in stone that you're going to sell this many units at that particular price. Production planning, inventory relocation, the examples continue. Basically, none of the textbook examples that you find exist in reality. As a matter of fact, I will say that single objective linear deterministic optimization is the rare exception and not the rule, which is what you might walk away from if you ever took an operational research course. So how do we extend MIP? That's the question. How do we do that? How can we get there? Well, there is this thing called machine learning. And it's fascinating. It means that rather than me trying to program something that will work well, can I teach the machine to teach itself? Can I allow the machine to learn how to do things better? And we started this in earnest in 2006. So I had a career grant at the time. I was working at Brown. And I figured, okay, look, Miss, a lot of the search decisions that I'm taking, I don't really know what I'm doing. I come up with some heuristics that make sense at programming time, but I want the machine to be able to actually learn how to do these things better. Okay, so let's talk about how we can use machine learning in order to improve optimization. How do we improve this search process that is going to try and find a good plan? That is the objective. So far, so good. So before we dive into this, we need to be on the same page of what machine learning is. Couple of points. Learning is not free. It requires experience. You need data, and then you need to invest some time in order to update your pattern matching, kind of the models that are there. Learning is not free. Then when you learned, your forecasts you're going to get are frequently wrong. They're not correct. Noise. There are certain things that you just can't predict properly. And then the most important piece is that machine learning itself doesn't tell you what to do. It gives you a forecast. It might say, well, there's a 60% chance of rain in New York today. Okay, does that mean I'm going to wear a raincoat? And does it mean I take an umbrella? Does it mean I guess it and just go out in a shirt? It doesn't tell you what to do. It only tells you a forecast with uncertainty. So if you take nothing away from this talk, then this sentence, then it was worth that you were here today. Machine learning is like counting cards. If you know blackjack and this, you don't need to actually know the rules or anything like this, but sometimes you could, if you knew what cards were already taken out of a deck, you could know that the deck is what is called hot. There might be lots and lots of cards still there that are worth 10. So, all the jacks, the queens, the kings, and so on, right? They're all worth 10. If you have lots of them, doesn't mean that you're going to win next time you play against the bank, but it means that your odds of winning have just gone up. So you have a very slight edge. This is what machine learning gives you, a very slight edge. Now, what would you not do in blackjack? I mean, somebody can tell you that the deck is hot. You're not going to bet all of your money on the next game. Because if you lose that, you lost all of your money and that's it. So just because you have a high expectancy of a gain doesn't mean that you want to put all of your eggs in that one basket. Or to put it in Roger Federer's words when he gave the commencement speech at Dartmouth was, well, I won 80% of matches, but only 54% of points. So what does that mean? It means that if a tennis match consisted of 1 point, Roger Federer would have won exactly 54% of his matches, not 80. What you want if you have a slight edge is multiple games. You want lots of them because you have a small edge that machine learning gives you, and you want to leverage this as many times as you possibly can. That is where machine learning comes in. You don't use machine learning that much in order to do one-off decisions. So you have to wonder, if you look at machine learning this way, why are people still suggesting to use machine learning for branch and bound, where I have few very high stakes decisions? Why would they suggest to learn during search? So while I am actually solving an individual instance, how I should branch, for example, because the most consequential decision that you're going to take is the first one at the root, when you have absolutely no experience. And for a long time, you're not going to have much experience before if you dive into the tree. And so basically, you don't know anything. Why would you do that? It's pointless to try and get an advantage this way. And then when it comes to our decision-making problems, say the pricing thing, why would people use, when they know that the machine learning just gives you an edge, it gives you an idea on where it is, but can be wrong, why on earth would people try and build plans for one predicted future? So this is what it means to use point estimates, right? So it will say, okay, so at this price, you will have this demand. I cannot base my plan on the idea that this is exactly what's going to happen. I have to build plans keeping in mind that, yeah, well, this might be my demand, but it might be a little bit less, it might be a little bit more. Okay? So what you want to use ML for is you want to use it often for many low-stakes search decisions. And when you're making the final plan, if you're actually evaluating a course of action, a plan of decisions that you can take, you want to take into account the uncertainty. So a whole mass of futures that could hit you based on your forecast, as opposed to just one, which you're going to woefully overfit if you do that. But that is still the status quo in operational research, to do it this way. Okay, so now what does it mean? Well, it means, okay, look, forget about this whole relaxation-based way of doing things. Let's use a primal method. So rather than knowing where I'm not going to find something that's great, I'm going to use a method that goes like, oh, look, here's an interesting plan that's already working halfway good. And here's another one, and that's also working reasonably well. Let's see if we can improve them. maybe independently of one another, or, take one and try if you can make some tweaks and make it even better than it used to be. Or I can recombine those plans. And I can say, maybe I can take this part of this plan and this part of this plan, and by combining them, I can have a better one. Now, what that allows you to do is you can hyperparameterize this methodology, and that's what we did. So you build, because no one search method is the right search method for all kinds of optimization problems. So what you want is that this way of searching, this primal method that you're having there, is parameterized in such a way that it takes its search experience while doing the solve into account, but that gets tuned offline. So basically, the learning is happening while you are solving similar problems offline. And then once you go into deployment, now you have to do it as a matter of course. You have good hyperparameters. But within the instance that you're solving, these hyperparameters do not directly steer what the method is going to do, but they only they combine kind of these hyperparameters with runtime features. Things like, how long has it been since I found an improving solution? When did I do a last restart? Have I tried to recombine these things yet? And these things, and this trajectory is different for every problem instance that you're going to solve. These things are specialized for the particular instance, whereas the hyperparameters that you're tuning are specialized for the entire class of problems that you're trying to solve with a method. So that means you can now automatically configure your optimization solver to make it the best potential primal heuristic that you can think of by using a computer to do it for you. The solver that we built is fully distributed, so that's another big advantage. Contrary to relaxation-based solvers, these primal methods parallelize very, very well. So you can suddenly throw compute at a problem, which wasn't possible before. You can solve multi-objective problems, naturally. You can solve stochastic problems, well, naturally. And you can solve non-convex, non-differentiable problems. Why can you do all of these things? Well, because a primal method is always working off of a complete current plan, and it can evaluate them and see whether another plan is better or worse than the current one that I'm having. So I'm not reliant on the fact that I can compute a very, very tight relaxation. This thing that tells me, oh, you're not going to find something there that's going to be good. This is what AI-based search is, and this is what we implemented, and that's the product that we're selling here at InsideOpt. All right. That's the preamble. Now the rest is all examples, and we'll see to how many we will actually get to. But if you guys have any questions and you want to raise them, please go ahead. I don't know, Jakob, whether you want us to take them while we do, but I'm perfectly fine with it. If somebody wants to interrupt me, it's okay.
Okay.
Cool. So are we good so far? We understand what we're doing. We're going to solve a couple of decision problems now, and if you have any questions, just interrupt me.
Samples would be great.
Yeah, exactly, right? So examples will make this easier to grasp now. So what are we talking about? So say you have a production planning problem. You run a supermarket, or say you're making sushi dishes, and you have two types of sushi dishes, 1 and 2. Typically, you have some constraints on how much you can produce. You have ingredients, you have only that many workers, right? So there are usually restrictions on how much you can produce. So this is what you see in constraints 1 and 2. So how much of sushi dish 1 we're going to produce is encapsulated in variable Q1, and how much of sushi dish 2 we're going to produce is in Q2. So think of it at quantity 1, quantity 2. And you see here your typical, constraints that you might have for limited production capabilities. So I don't know, maybe sushi dish 1 needs salmon, and sushi dish 2 also. But in sushi dish 1 there's like 3 pieces of salmon, and sushi dish 2 there's 4 pieces of salmon. But I only have 60,000 pieces of salmon. Good. So, right, and I can't produce more than 3 Q1 plus 4 Q2 needs to be lower equals 60,000. This is what that means. Okay. So the other thing I have is, well, that I have limited demand. So I'm estimating my demand. And I'm doing here what I just told you should never do, which is I take my forecast at face value. I'm going to say I am not going to produce more. I'm not going to be able to sell more than 7,000 units of sushi dish number one. Okay, so my sale for sushi dish number one, so think S sale, sushi dish number one has to be lower equal to quantity I'm producing. Well, naturally, I can only sell what I'm producing, but I'm also not going to sell more than 7,000. And the same thing for sushi dish number two, just there I can sell 10,500. Apparently, that's my estimated demand. And now I have another thing here. So what are these E variables? It's excess. So if I produce sushi dish number one, and I'm not selling as many as I produced, then I'm going to have excess. So my excess would be equal to Q1 minus S1, right? So the quantity I produced minus the ones that I sold. Now, why is excess important? Well, because now I produced a sushi dish that I have to throw away. So I'm not making a profit on selling it. I actually lost all that I put into that thing, including the waste removal. So that brings us to the objective function. Well, the objective function is we make 30 cents profit on sushi dish one, 45 cents on sushi dish number two, but everything that went into that thing cost me $2.70 for sushi dish one and $6 for sushi dish number two. So if I produced more than I wanted, then I'm losing that money. Okay, so this here, what you're seeing here is a good old-fashioned linear, well, you probably want only whole sushi dishes, but it would be an integer program, right? So you want integer values for S1 and S2, and then E1 and E2 will come out integer naturally. Okay, so now what we can do is we can solve this, right? So we can solve this, shove it into your ordinary MIP solver, and what you're going to get is this solution. Make 6,000 sushi dish ones and make 10,500 sushi dish two. And then the thing tells us our profit will be 6,525. Okay, that is the case if our demand is indeed 7,000 and 10,500, right, for the two dishes. But what if that demand isn't set in stone? So say that I multiplied this demand with a normal distribution. Expected value is 1, so meaning the expected value remains 7,000 and 10,500, but now I might multiply it with 0.9, for example. So standard deviation here is 0.1, right? So if I'm one standard deviation below the expected value, I wouldn't sell 7,000 of dish number one. I would pay. I would only be able to sell 6,300. Or and then of course the factors for the two dishes would be drawn independently from one another. Okay, so if I do that and now I simulate this solution, so say I made 6,000 of sushi dish number one and 10,500 of sushi dish number two, what is actually the real profit that I'm going to make if I run this 1,000,000 times? Well, that ain't 6,525. It's only 3,756. Why? Well, because I'm right at the edge for sushi dish number two, which cost me $6 if I produced one too many of them. So I'm right at the edge of what I thought I could sell. And well, half of the time I'm not going to be able to sell that much, right? Because my estimated demand was a little bit too high. Yes, an expectation is 10,500, but on average, it isn't. So suddenly you're losing a lot of money. And if you look at the 10% quantile, so if you take out of that million scenarios that we ran over here, if you take the worst 100,000 scenarios, the average over those is you lose 2,223. So if you go into a business and you come with a mindset of an OR person, and you say, I'm going to optimize here, and you show them, hey, you're going to make 6,525, and everybody goes like, wow, that's 10% more, or it's 20% more what we're currently making. Awesome, good job. There will be a risk manager there, and that risk manager will run a simulation of the solution that you're proposing, and he will laugh you out of the room if he sees a number that says, well, in 10% of our cases, we're going to lose $2,200 with our production. Not happening. So now what you could do, and what I see companies do, is, well, okay, so they come up with a MIP solution, it goes to the risk officer, he does a simulation, or she does a simulation, finds this is unacceptable, we can't do this. And then it's really unclear how that top arrow back is going to work, right? So how do I adjust my MIP model parameters in a meaningful, a rational way in order to get a solution that next time I run the simulation, hopefully my risk officer is happy and I'm still saving some money, right? Because that's the objective, right? Is to make a rational, good decision under the uncertainty of me not knowing exactly what the demand is going to be. So let's change it. So instead of saying, look at constraint 4, we used to say S1 has to be lower equal 7,000. Well, what if we say it's lower equal D1, and D1 is a variable that varies normally with the expected value 7,000 and standard deviation 700. Right, and similarly, what if sushi dish number 2, the demand for it would be a random variable that is, yes, on expectation 10,500, but with normally distributed with standard deviation 1,050. Okay, so I can optimize this. This is the solver that we built. So the solver is called Seeker. So if you look at this one here, you see, oh, good. My mean is no longer 3,756. It's 5,550. And if I look at the 10% quantile of the solutions that Seeker provides, it's still above 5,000. Now, the cool part is, so say that you don't really know how the demand is going to vary. On the right-hand side, I give you a very, very different noise curve. Okay, so here I'm saying, well, okay, so my noise, how I'm deviating from my estimated demand, is actually skewed to the left with an exponential. So again, expected value is 1. So my expected values are still going to be 7,000 for sushi dish 1 and 10,500 for sushi dish number 2. But of course, the way how it varies, the way how this exponential, the negative exponential function that you see over here dips into the demand is much more aggressive than with a normal. And you see that here. So Seeker now, with the best setting of production levels, only gets you to about 5,100 with a 10% quantile at 4,200 roughly. But that's a heck of a lot better than what you would be getting with PTO. So PTO is predict and optimize, right? So you just take the 7,000, 10,500 at face value, run a MIP solver, and always get the same. All right, I mean, for that thing, it doesn't even matter what the shape of the distribution is. It will always come back with 6,000 and 10,500, right? Because the expected value is always the same. So now you might say, well, okay, but I don't know what my curve actually is. Well, look at the solutions that Seeker gives you. The noise curve is completely different. How much money you're making is also slightly different. But the answer of how much you should be producing is almost the same. It tells you very clearly, stay away from the 10,500, which is our expected demand, because the risk is too high. You shouldn't be doing this, right? So stay away from it. So it gets you down to somewhere 8,900, 8,800. It doesn't really matter, but stay away from 10,500. And that, of course, offers room to produce more of sushi dish number 1. And whether you're going to produce 6,100 or 6,160, that's not the important point. So this is what we're finding. You cannot ignore the uncertainty in the forecasts. But when it comes to estimating exactly how my estimates will vary, you will have a lot of leeway. As long as the solver is forced to come up with a solution that works for a reasonable probability mass of futures, chances are that the futures that will really happen will be in there. So it doesn't really matter that you know that noise curve precisely or that all of your noise parameters are perfectly correct. But by all means, do not use PTO. So let me hammer this one down. The results obviously here would depend on the number of scenarios, right? So what you see on the x-axis is if I take randomly 10 scenarios, right? So I sample 10 demand scenarios for my sushi dishes, and now I see a value of how good am I actually doing, right? So I optimize for those 10 scenarios, and I see a value. I get a value back that says, well, for those 10 scenarios, you would expect on average to do this well. And then I can evaluate those against 1,000,000 scenarios on the left-hand side, so on the y-axis, and see how well this actually does, right? So 1,000,000 is that's really enough in order to have a very good idea what it is. So, okay, so here we sampled 10 scenarios, and this is a good one, right? So these were good 10 scenarios. It estimates itself around 5,500, and I don't know, the real value is 5,450. Fine, okay? But now you sample 10 other scenarios, and suddenly you think you're at 6,200, but in reality you're at 5,200. You sample another 10 scenarios and you're all over here. We repeated that 100 times. This is what it looks like. So very clearly, if you're sampling 10 scenarios, you might be very, very off in your assessment on how well you're actually going to do. Okay? So let's ramp up the number of scenarios, because this is the name of the game here. How can you ramp up the number of scenarios without paying a huge computational cost? And that's what we figured out. That's what we're selling. So you see here the picture that I just gave you, and you also see where predict and optimize is, right? So this is the industry standard. This is what everybody's doing. Just make a point prediction, forget the day's variance in my forecast, just optimize for that one future. And this is the solution you're going to get. Well, 10 scenarios is already a heck of a lot better, right? So as you can see by being much, much higher on the y-axis here. But this varies too much. So let's ramp up the number of scenarios, and you see that as you're ramping this up, you get a much better feel on how well you're doing, right? So the most important thing is that the variance in the y-axis goes away. So who cares that you think it's very, very far to the right, which might be massively better. So here, for this point, you might think you get a 5,800. In reality, you get 5,500. Okay, doesn't matter that you're off. In reality, you're getting something that's very, very close to what you can achieve over here. In Seeker, we frequently use 10,000 scenarios, and we found a way in order to get to that level of resolution without actually running 10,000 scenarios, of course, because that takes way too long. And this was for the normal noise. For the exponential noise, it looks exactly the same, right? So you by doing lots of scenarios, you can rein the whole thing in and solve this problem. Now, what the solver also allows you to do now, I mean, if you have that many scenarios, you might as well do risk adjustment, right? So now you might go like, well, I'm not just interested in having a high expected value. So in this case here, this curve you see on the right here is the one that gave you the 5,500 estimate for your profit. And this one here is one where we optimize at the same time our conditional value at risk of 5%. And the expected overall profit that we would be getting over everybody, not just the 5% worse. Multi-objectively, of course, because the solver allows you to do that. And this looks like, my goodness, we're taking a huge hit here on the upside, but actually the expected value of this guy here, the left curve, is maybe $100 or so on expectation, less than what this one is. So this is 5,550, this is 5,450. But at the same time, the conditional value at risk goes up tremendously. As you can see, if you zoom into the space here under 4,000 on the right-hand side here, you see that our probability density of hitting something that, where suddenly we would only be making a profit of $1,000 instead of the 5,450 or so that we're expecting, is halved. And that is why the expected value is not so much worse, even though we lost a lot of the upside here. Okay, so this is what you need in order to run a business. This becomes now predictable. It becomes something that is robust, that is not going to be brittly breaking down every other day that you run your operations. And it allows you to up your efficiency with your decisions that you're taking operationally in your business every single day. So I can move to another example now, but maybe this is a good time to take some questions if you have them.
Okay, just to clarify, so you're running not one but multiple scenarios, and you receive the average results over all scenarios and apply them to each particular case?
Well, I mean, you decide. So when you write the model, so I do want to bore you here with actual Python code, but when you write the model and you have a data point that is stochastic, right? So, I mean, you can put your own distributions in there. They can also be multi-dimensional distributions, right? So joint correlations of multiple uncertain data points, it's all fine. Or you can say, hey, I have multiple independent random variables. Some of them are gammas, others are normals. All fine, right? So, but now, if you derive any terms from there, so if you're saying, okay, so I have an uncertain data point. So say, for example, the lead time as I'm replenishing my inventory, right? The lead time is off. Right? Sometimes it takes 8 weeks for the ship to arrive. Sometimes it's 9, and occasionally it's even 10. Okay. So now you're in a scenario. So you see what lead time it currently is, and now the result that you're going to get. How was your fill rate? How much inventory did you carry, and so on with what you were optimizing for your plan. Is of course now also distribution, because it kind of depends on, well, did this arrive in after 8 weeks or did it arrive after 10 weeks, right? Makes a big difference on your fill rates. So everything that you're going to get after you derive something from a distribution is going to be a distribution again. And now the question that you're asking is, well, do I always have to take the expected value? No, you don't, as you can see here, right? So in this case here, I'm aggregating. So before I can constrain this or before I can optimize a distribution, I need to take a statistic over it. I need to say, okay, so am I trying to optimize my expected profit? Am I trying to optimize my 25% quantile profit? Am I trying to do my 50% quantile profit, right? So on the median. Am I trying to optimize my conditional value at risk at 5%? You tell the solver which one to take, right? So there's a number of different ways, and I can take statistics over a given distribution, by the way, including the probability mass itself. So if you would think, God, for my cash flow, it's awful if I'm not making $4,000 profit because I have salaries to sell and whatnot, the salaries to pay and whatnot, then you can say, well, measure me the total probability mass for everything that is lower than 4,000 and minimize that probability mass while keeping my expected value high. You can do that too. So it is completely up to the modeler to say how they want to aggregate over a statistic before they constrain or optimize against that value. Pretty neat, huh? You see now why I think it's revolutionary.
Yeah, interesting.
Yeah, it is. Okay, so I could bore you with facility location right now. I'll very briefly go over this one here because I have more interesting examples. But this is a classical one. No stochasticity in there. It's all just, okay, so I have a couple of locations where I can open a facility or not, right? You see that here. And now I need to assign my customers to each one of those distribution centers. In this case here, apparently it's fine to split the demand. Typically, you don't want that. You want to assign one client to one distribution center. Okay, so then you can't go over the capacity of the distribution centers, and you're supposed to decide where you're going to open the facilities and how you're going to assign these customers. Now, a traditional way to do this is to write a MIP like this. It will kind of bore you with this, but essentially you get a binary variable for every customer on how you're going to assign them to a facility, right? So this is going to be 1 if you assign this customer to one facility. And then you can't go over the capacities, and you have to pay the opening cost for a facility if you assign at least one client to that facility, right? So that's kind of how it goes. Okay, now we had a client that came to us with this. We have 20,000 clients. We do not know where we're going to open those facilities, but we want you to minimize the have-assigned distance that our clients have to the facilities we're going to open. So you're not being told where to open, which is mandatory in the mixed integer programming formulation. You need to have a set of, well, I could open it here, could open it there. And then secondly, I have 20,000 of those. If I have 20,000 clients and distribute them over 50 potential, I'm sorry, I don't actually know what that is. Oh, there we go. The wife, not right now. If I have 50 potential locations for every client and 20,000 clients, that means I have 1 million binary variables in my model. I ain't gonna fly. Plus, I have a totally nonlinear distance in here. I mean, I could pre-compute the distance matrix, but it's not this really doesn't fly. So what do you do in Seeker? Well, in Seeker you would say, okay, look, let me freely choose where I'm going to put my facilities. Pick a longitude and latitude, right? Put one there. And then for every client, you're going to compute the two closest facilities that you could have. Okay. And then you put a threshold. I mean, so the reason why this isn't a straight line and why this doesn't look like a Voronoi diagram is because we're using the Haversine distance, right? So there is the Earth is a little bit curved, contrary to what some people think. And that means that this line is not going to be straight. But essentially, what this is saying is, well, the solver gets to decide if your second closest facility isn't that much further away than the closest one, then assign me to it. Like this, you allow the solver to draw these lines closer or further away from one of the facilities that was taken. And you can see, for example, here, right? So the Voronoi cell between, right? So if you look at these two facilities, you would expect something like, the line to run somewhere here, but it runs massively further to the right because somehow somebody set this threshold here to say, well, if you are if you are on this side over here, and you are not that much further away from this facility than from that one, then please go to this facility. So like this, you can make use of facilities that can handle more capacity than others that could only handle less capacity. So now what is the solver allowed to do? So this is just the text of the description, what I was just said. What is the solver now able to do? I mean, this is a continuous variable, right? So it's a continuous threshold that says, well, if your second closest facility is no more than 0.52 away than the closest one, then assign it to that one. And you have that for every pair of facilities you're going to open. Okay. So the solver can now, just by adjusting this one parameter, so in this case, we set it from 0.45 to 0.55, can reassign all of these points directly to this guy over here and away from this guy here, just by adjusting a single parameter in the solution. And in fact, so this is what it looked like before, right? So this was the threshold at 0.45, this is the threshold at 0.55. All of these guys, right? So all of these binary variables in the MIP have just been set from 0 to 1. Right? They were all set, well, actually there's lots of xij's here, and they went from xij to xik, right? So which was 1. This is really what happened here implicitly by adjusting a single continuous variable. Completely undoable in mixed integer programming. So let's compare the models. If you do the Seeker model, you have free choice of locations. You can just choose a longitude and latitude. Say you want to open 10 facilities, you get 20 continuous variables for that one. Okay, and then for each pair of those, so n choose 2, which is 45, right? So if you had 50 locations, I'm sorry, if you open 10 locations and you take 10 choose 2, you'd get another 45 pairs where you have to set this continuous threshold, right, for the Voronoi. So it gives you 65 continuous variables. On the MIP side, I would have to fix myself to 50 locations. I get 1 million binary variables. Do we even have to talk about who's going to win this race? It is very clear. I mean, in Seeker, within seconds, you get reasonable solutions. And in MIP, you can wait 10 days and still not have anything that looks any way reasonable. So quadratic assignment is the typical go-to thing. I mean, I admit that this particular problem that people came up with here is not very known, but quadratic assignment is, so you have n locations, n facilities that you have to put somewhere, and you know how much traffic there's going to be between them. I'm going to wrap up in a moment, Jakob. Now I have to assign them, right? So this is a well-known standard deterministic linear integer programming formulation that exists for the thing. And of course you can run this, right? So you're looking for a permutation here, who goes where. You can run this on a solver like Gurobi. This is what it looks like on the Taya instances, instance by instance, after 60 seconds. You see what the gap for Seeker is on the y-axis. You see what the gap for Gurobi is on the x-axis. Not a single instance where Gurobi has a better solution after 60 seconds than Seeker. Not a single one. And after an hour, it looks worse. Actually, it's like, we had to tilt this diagonal here because otherwise you wouldn't be seeing anything. Right, so Seeker is down now in the worst case here at a gap to the best known solutions for these instances of 1.8%. Whereas, that's the worst case, whereas we had to block at 10% here just because you wouldn't see anything anymore for Gurobi. If you do the estimate, so if you took the performance of Gurobi after an hour, and you stop Seeker the moment it finds something that's strictly better than what Gurobi finds after an hour, you will find that Seeker is then 1,000 times faster while closing 26.7% of the optimality gap. That's the performance gap that we're talking about here. 3 orders of magnitude. And this is not because we are so awesome at implementing this thing. It's because this particular problem does not want to be solved with MIP. And that's what I'm trying to say. It's like there is a whole world of problems that do not want to be solved with mixed interprogramming technology. And now there is a solver with which you can tackle that. Okay, so that's really all I wanted to say. There's much more in the slides where you can see like a patient journey that we're optimizing, what we're doing for train yarding and whatnot. The only thing that I will say here at the end is there is a tool for you right now in order to break into this big space of problems that were completely out of reach before, that you can now tackle with a new tool that is available for you. And I would appreciate if you guys would contact me on LinkedIn, connect with me. I always like accepting new connections. There's a newsletter that you can sign up to. Maybe take a photo of this. I don't think I put that into the slides that you find on the DecisionCAMP web pages. And of course, visit our webpage at InsideOpt.com. There is a free version on the Google Colab that you can use, and you can test it all yourself. A lot of these newsletter examples also have collabs with them, so you can go directly into the code, see what the models look like, and play around with the tool.
Okay, thank you. Thank you very much. It's very interesting, and people who work in optimization world, they actually, when we do practical applications, we know that uncertainty is one of the major problems, and the search for optimal solution frequently is a wrong search. We're trying to find practical solutions that addresses not optimal solution in one particular point of time, but over time. And this is what you described. It's certainly much better approach. And that's why, by the way, your presentation demystifies optimization in general, where people are afraid that they have to be optimization gurus, you need PhD to apply this. You can do this in much, much more simple way. Sure. And that's why actually in last 10 years, people started to incorporate optimization solvers inside decision intelligence frameworks in general. And your examples with InsideOpt is really, your Seeker could be a good candidate for this, for different people who wants to add optimization to their platforms. Okay, any questions?
Thank you, Jakob.
We have one question in the chat. You can read it, or Michael, you can ask.
I'll just ask. Basically, I'm asking what I'm reading, but I guess that I'm thinking in terms of, for most of these problems, it's not so much we have the freedom to build as much as we want to, but rather it's going to be an evolutionary process to incrementally add some things. And I'm just curious, recasting, I think the product is fascinating, but recasting it in that form of what do we incrementally do today? Can you respond to that?
Yes, absolutely. So, this is what Warren Powell calls sequential decision optimization, and this is the reality, right? So, if you're doing inventory optimization, for example. Yes, sure. You want to know your thresholds, right? So what are your mins and maxes next week? But when whatever you're going to order is going to arrive in 8. So you're going to simulate out if you use a certain policy, right? So now you go away from a strict plan to something that is somewhat parameterized to how the situation is going to evolve, right? So you build a policy. And you're going to evaluate that policy potentially against the whole year of running your warehouse. But then you're going to use it for the next week or 2 weeks or something like this. And then you're going to re-optimize again with your updates on, how has my demand forecast changed dramatically, right? Has new inventory come in that I didn't expect, or things like that. So if you did what again a lot of people currently do is to I take today's week, right? So week today, and I optimize my decisions for this week. Then what I'm woefully forgetting is that I'm not just optimizing my results for this week, but I'm also setting myself up for next week, right? So my starting point next week is going to look dire if I'm trying to optimize the last pin out of my current week. And so you need to optimize this over some time. If you look at the newsletter, there's a couple of examples. So for example, you can use Seeker to do a form of reinforcement learning where you actually learn a policy. But contrary to reinforcement learning, which can only optimize the expected value, you can also do risk analysis with this thing. So if you go to I think it's called the Great Auction Gamble or something like that. That was a puzzle that we had there. So a series of auctions that you had to do. What you will find there is that, yes, you can optimize your expected value, and it looks like, I don't know, you gain like $2 million or so, but then you do the analysis with Seeker and you find that, well, actually in 51% of the cases, you're going to lose money. And that is very important to know for business. It's not like what my expected value is and that my policy optimized it, but also what is the downside? What's my risk that I'm taking on? And of course, you want to find a policy that somehow balances the two. Very good question. Yeah.
Okay. Thank you.
Yeah.
More questions? Okay. I just take a moment to stress what you just said. It's really very, very practical things. And I have this similar experience when we build, for example, system for warehouse with limited fleet, and they have to send 40 or 50 trucks in different locations. And our objective was to minimize total number of trucks. But if we do optimal solution on Friday, then on Monday, we will suffer a lot, right? That's exactly what you just pointed.
Yeah.
And so this is certainly a very practical approach. And only one point I want to ask or to make. You said, like, people can take from your presentations that you're 1,000 times faster than, for example, Gurobi or other solvers. It's not probably correct. It's because it's a different approach. Right? You can apply a lot of different solvers, Gurobi, Cplex, or open source solvers, right? Your approach more generic, and you actually, this is the point what I'm taking from here.
So absolutely. So I mean, the point on the QAP was, even if it's single objective, linear, and just a good old-fashioned IP that's been in the books for at least 40 years, right? QAP has been studied extensively. The reason why we're 1,000 times faster than Gurobi, and by the way, 50 times faster than Hexaly, which is another primal solver, is so on Hexaly, it's because we're better than them. On Gurobi, it is because the problem doesn't want to be solved with a MIP. And there are certain problems that you definitely want to solve with a linear programming. So, multi-commodity flow, for example, I would not dream to do with Seeker, which is why, by the way, if you have parts of a problem that are, for example, multi-commodity flow, you can nest a linear program inside of the Seeker model. So you can say, well, I'm going to take the high bits decisions where I'm going to put my facilities, but then how I'm going to route things, I use a linear programming solver in order to do that. And it's directly in the model. directly, right? So it's not like we're saying we're 1,000 times faster than Gurobi. What we're saying is, well, number one is they're not the fastest solver in the world, and number two is there is a class of problems for which MIP is completely and utterly useless, and you want to use a different tool for that. That's what we're aiming for, not to compete with MIP, but to give you a tool that extends what you can apply optimization to.
Okay. Meinolf, we can talk about this a lot. It's extremely interesting topic for a lot of people, but we have limited time, and we appreciate your presentation, and you will bring more attention to decision optimization in general. Thank you very much.
Thank you, Jakob.